Imagine you fire a single particle of light, just one tiny photon, toward a wall with two small slits. No one is watching it. It passes through, and something impossible happens. Instead of acting like a tiny bullet, it spreads out like a wave, creating an interference pattern on the screen behind it. A pattern that only waves can make. But here's where reality starts to break. The moment you place a detector to observe which slit the photon goes through, the interference pattern disappears. Suddenly, the photon behaves like a particle. It chooses one slit, it leaves a single mark. It acts completely differently. So the question that shook the foundations of physics is this: how does the photon know it is being observed? Does it sense the detector? Does it receive information from the environment? Or is something far stranger happening? Welcome to one of the most mysterious puzzles in quantum physics, a puzzle revealed by the famous Double-Slit Experiment. In this series, we are not just talking about light, we are questioning reality itself. Because if a photon changes its behavior when observed, what does that say about us? And what does that say about the universe? Long before we had lasers or quantum physics, there was a man named Thomas Young. Thomas Young was not just a physicist, he was a polymath. A man fascinated by how the world works. He studied medicine, languages, and most importantly, light. In the early 1800s, the common belief was that light was made of particles, tiny little bullets traveling through space. But Young had a different idea. He believed light behaved like waves, spreading and overlapping, creating patterns. To prove this, he designed a simple yet brilliant experiment. He placed a barrier with two narrow slits in front of a light source. Behind the barrier, he placed a screen to observe the light pattern. Then he shone light through the slits. What happened next was extraordinary. Instead of two simple spots on the screen, light formed a series of bright and dark stripes, an interference pattern. It was as if the light split, passed through both slits at the same time, and interfered with itself. This single experiment shattered the particle-only theory of light. It was the first concrete proof that light behaves as a wave. Young's experiment wasn't just a small discovery, it was revolutionary. It laid the foundation for quantum physics a century later, when scientists discovered that even single photons can produce interference patterns. This is where the story gets even stranger. Photons, when sent one by one through the slits, still form the same wave-like pattern, as if each photon knows about the other slit, even when no one else is there. And this tiny, seemingly simple experiment would later open the door to one of the greatest mysteries in quantum mechanics. Does the photon know it is being observed? Imagine this, a photon, a tiny particle of light traveling alone in a dark room. There's the same double-slit setup Thomas Young used, but now we are sending one photon at a time. No crowd, no waves, just a single photon. You might expect it to act like a particle, hitting the screen in one predictable spot. But slowly, as more and more photons are released, a familiar pattern emerges. Bright and dark stripes appear, the same interference pattern from waves. Each photon alone somehow interferes with itself. It's as if the photon explores both slits simultaneously, knowing all possible paths. Now comes the twist. Scientists place a tiny detector at the slits, just to see which slit the photon passes through. Suddenly, everything changes. The interference pattern disappears. The photon behaves like a particle. It chooses a single slit. It leaves a single mark. Observation has changed reality. This is the famous observer effect. It raises questions that boggle the mind. Does reality exist before we observe it? Is the act of measurement creating the outcome? Does the photon know it is being watched? And it gets even stranger with the delayed choice experiment. In this version, the decision to observe is made after the photon has already passed the slits. Even then, the photon chooses whether to behave like a particle or a wave, as if it knows its future, changing what happened in the past. Quantum physics is no longer just about particles and waves. It is about information, observation, and the mysterious connection between past, present, and future. The photon's behavior challenges everything we think we know about reality, space, time, and causality. And that, my friend, is why the double-slit experiment is not just a chapter in physics. It's a window into the mind-bending mysteries of the universe. Let's step into the world of John Archibald Wheeler, a brilliant mind who took Young's experiment into the future. Wheeler asked a mind-bending question. Can the future choice of measurement affect what already happened? He designed the delayed choice experiment. The setup looked familiar, a photon traveling toward a double-slit apparatus. But here's the twist. The decision to observe which slit the photon goes through could be made after the photon has passed the slits. You might think the photon already decided its path. But in quantum mechanics, nothing is decided until observation. If the experimenter chooses to measure after the photon passes, the photon behaves like a particle, retroactively. If the experimenter does not measure, the photon behaves like a wave, forming an interference pattern. It's as if the photon knows its future and shapes its past accordingly. Wheeler called this the delayed choice effect, a direct challenge to classical notions of time and causality. The experiment forces us to ask, is reality fixed before observation? Or does measurement reach back in time, shaping what already happened? Can the universe itself be dependent on observation? No one fully understands it, and that's why this experiment is still considered one of the deepest mysteries in quantum physics. So what can we take away from all this? The double-slit and delayed choice experiments tell us something extraordinary. Observation is not passive. Photons and perhaps all quantum particles do not follow a fixed path. They exist in multiple possibilities until measured. Our act of observing seems to collapse these possibilities into reality. Time, space, and causality are no longer absolute. The past, present, and future can intertwine in ways we cannot intuitively understand. Even today, physicists are puzzled. The universe is stranger than we can imagine. The double-slit experiment, Young's insight, and Wheeler's delayed choice remind us. Quantum physics is not just about particles and waves. It's about mystery, observation, and the limits of reality itself. And as you watch the photon dance between wave and particle, remember this. The universe is not just out there. It may be watching back. And here's the truth. Even today, no one can fully explain why a photon behaves like a particle when observed and like a wave when it is not. We can describe the mathematics. We can predict the probabilities. We can build the experiments. But the deeper question still remains unanswered. Why does observation change reality? Physicists have debated this for over a century. From Copenhagen to many worlds interpretations, from Einstein to Wheeler, yet the mystery survives. The photon does not tell us its secret. It simply behaves as if reality itself depends on being seen. And maybe, just maybe, the universe is far stranger than we are ready to accept. If you enjoyed diving into the mysteries of quantum physics, if this video made you question reality itself, then make sure you subscribe to this channel. Because here we don't just learn science, we explore the limits of existence. Subscribe now and let's uncover the next mystery together.